Okay, so remember we determined that column minimizing will play along the lower envelope and that rows maximizing will try to play at that intersection point, right? That's the highest value of the game. Okay, so what are we going to do? We're going to look at the two strategies that intersect at that point, the red and the blue, which is points 1 and 3. Okay, so I'm in the workspace now, and the key thing is this function has to be defined. And I have our main example, the same thing that we were looking at over here. Sorry, do I have it? There it is. It's the right way. I'm sorry, this is the correct matrix that we're looking at. And let me jump over. Okay, so if this is the correct matrix we're looking at, notice that the 2, the 4, and the 1 should be the values, right, that go with the x-coordinate of 0. And I'm just calling them points 1, points 2, points 3, so I'll know what they go with. And then the 1, the 0, and the 5 go with the x-coordinate of 1. All right, so I'm graphing these, and notice for the moment, till I see the graph, that I have all of the algebra to find the intersection point and display it. I have it commented out with a hashtag to start the line. That's intentional. Why? Because I don't yet know what the solution is. Um, so let's run this. And notice that we get the strategy graphs that I showed before, right? And what do we want? We want the intersection point right here. And to find that intersection point, I am going to uncover the correct values up above, right? So what am I going to do? I'm going to come through here and I am going to delete out these comments. So that will calculate the slope and intercept, and that, sorry, was supposed to stay there. Right? And then this is going to calculate the point of intersection. The limit denominator actually reduces the fraction to lowest terms. And then the plot is going to do it. But what do I need to do? I need to make sure that I'm doing the right points, right? And we said that the intersection of 1 and 3, right? Those were the two lines that we needed. Strategies A and B. So, and I did them in order, so that will work. And what's that going to do? That's going to create the yellow dot in this intersection, right? And what's it going to do? If you notice, it is going to display on the legend what the values are. So let me get rid of the highlighting. And what's going on? Well, you'll notice that I have the legend, the part of the legend that would show the intersection point, I had that turned off. Why? Well, we didn't need it yet. Now we need it, right? And if I scroll down, you can see that we know that the intersection point is 1/5, 9/5. Okay, so the value of the game, right? The value of the game is 1.8 or 9/5, right? And we know that the percentage of time Rose should play strategy B is 1/5, right? She should play 4/5 A, 1/5 B. And there we have the value of the game, right? And we have the optimal strategy proportion. And you're like, well, that tells me what Rose should do, what should Colin do? Well, that's where we remember that we can solve a 2x2 with oddments. All right, and what 2x2 are we looking at? Well, we take the game, right? The 2x2 game with just strategy A and C for Colin, and then we can solve that with oddments and find Rose's optimal strategy again, which will be 4/5, 1/5, and the game value of 9/5. Okay? So that's how the strategy works. That's how we figure out which strategies are active and how we figure out the game value. Okay? And here's an example. 135, notice that the 1, the 3, and the 5, they're in row A, so we're going to make them the y-intercepts. And then the 6, 2, and 1 from the second column, 6. Oh, wait, I need to make that a 2. 6, 2, and 1. Okay, so 1, 3, 5, 6, 2, and 1. For the moment, it can calculate that stuff, but let me turn off the scatter plot that will plot that point. Why? Because I don't need the point of intersection right now. Let me just run this and graph, right? So what am I looking at? I'm looking at, again, Colin has more than 2 strategies, so Colin's going to try to play along the lower envelope. And we're in a very similar situation. Notice that this graph has 3 different sections, right? And Colin will try to play the blue strategy when possible. The thing of it is, Rose isn't going to make that optimal for him. Rose is going to pick the value here, right? That's the place along the x-axis Rose wants to play to maximize what will happen. So Colin won't want to play the blue strategy because even though if Rose were playing a lot of the B strategy, her B strategy, it would make sense where Rose is going to play over here, right? The blue would actually be much, much better for Rose and much, much worse for Colin. So Colin is going to be forced to play red and green. Okay? And red and green, let me get rid of the drawings I made. And then red and green are going to be 1 and 2. Right? So I can go back up here, right? And now my intersection, right? 1 and 2. All right, and I can get rid of that hashtag so it'll show that point. And it shows the intersection, okay? So 1/3, so what does that mean? The 1/3 in the x coordinate means that that's the percentage of time Rose is going to play B. So her optimal strategy pair is 2/3, 1/3. She should play 2/3 A, 1/3 B. And when she does that, Colin, trying to stay on the lower envelope, will play strategies A and B, and the value of the game will be 8/3. Okay, so that's how we do it. And again, to get Colin's strategy mixture, do we have to use oddments? Yes. We'll create the game with strategy A and C for Colin, take the oddments, and go that way. So another example, rows 1, 3, and 11, 8, 5, 2. Notice that the 1, the 3, and the 11 are row A. The 8, the 5, and the 2 are row B. And notice that we're intersecting strategies 2 and 3. Why? Well, I'm not going to do all of the work. I'm going to do it all at once. And we see, right? And I think I need to change the names here. Hang on a second. Because, no, this is still with Rose having 2 strategies. Colin has 3. So Colin is the one who is selecting the lower envelope. Rose is going to choose the highest point, the maximum point along the lower envelope. That's the x coordinate that's going to give her strategy proportion. So she's going to play 8/11ths B. That'll leave 3/11ths A. And the value of the game is 49/11ths. And again, to find the correct strategy mixture for Colin, right, we need the 2x2 subgame with Colin's strategy B and C. Okay, and quickly one more, where Rose is the one that is choosing the strategies, and I will, at the moment, again, I'm going to get rid of the point of intersection. Why? Because we don't know which one it should be, perhaps. 2, 3, and 5 are going to do the same thing. The 2, the 3, and the 5 are going to be in column A, so we're going to put them as our y-intercepts, and where we're crossing the line x equals 1, we're going to have a 4, a 1, and a 0. All right, so again, trying to keep it straightforward so that the column A strategies go first, and the column B strategies go second, trying to keep things nice and neat. Sorry, let me try that again. Okay, so here we go. Those strategy graphs look like the ones above. Okay, hang on a second. 2, 3, and 5. 2, 3, and 5. 4, 1, and 0. So we should have that ready to go, and this should be the right thing. Except what are we doing now? We're playing along the upper envelope. Why? Because Rose has 3 strategies and Colin only has 2 now. So with Rose's 3 strategies, right, she's going to try to play along the upper envelope. What's Colin going to do? Colin is going to try to minimize the value along the upper envelope. Okay, so when he does that, that means the strategies A and C are active, right? Strategy A, red, strategy B, C, blue. Okay, that's why we've chosen points 1 and points 3 to do our algebra. And when I take the hashtag off the thing that plots the intersection point, I have it showing up on the graph. And if I scroll down, you'll see, hang on, scrolling down, you'll see that we have the correct values for the point of intersection. So what do we know? We know Colin wants to play 3/7 B, so he's going to play 4/7 A, 3/7 B. And the value of the game is going to be 20/7, which is 2 6/7, right? And that is the y value of that point. The x coordinate of the point, again, is the percentage of time that Colin is going to play strategy B. How are we going to solve for Rose's values? Well, we're going to create the sub-game, the 2x2 sub-game, where we only look at Rose having strategy A and C. That's how you use the graphical method to solve 2x(n) or n/2 games. Hey everybody, I'm going to present a simplified version of the graphical method to try to help clear up some of the difficulties that people are having. And so here we go. The idea being that we have an n/2 or a 2x(n) matrix game. And the key thing is that we know that the solution, if it doesn't resolve to a single equilibrium point, right? If there's a mixed strategy solution, it's in some 2x2 subgame, right? And we know this because of the square matrix solution principle in any n/n game, right? It's the solution to that n/n is going to be some square matrix, some subgame that, if I put together the subgame, will be a square matrix where both players have the same number of active strategies. All right, so then what we're going to use the graphical method to do, the main key is we're going to find the correct subgame to solve. Can we reduce by dominance? Sure we can. Sometimes it's not possible. And also at this point, I'll mention that sometimes our matrix game solvers, the ones we find online or the one that's coded in our workspace, for example, sometimes they don't solve correctly. Why? Because the solution by dominance isn't always there. But we have the graphical method, which allows us to choose the proper subgame based on whether or not the players will be playing along the upper envelope or the lower envelope of that graph. So what we're going to do is we're going to make a linear graph for each strategy for the player who has more than 2 strategies. And then we'll have n strategies represented by a single line, remembering that Rose is maximizing. So if Rose has more than 2 strategies, she's going to do her best to play along the upper envelope. She's going to choose strategies that will help her play along the upper envelope. Those are the higher values, and she's trying to maximize. If Colin is the one with more than 2 strategies, he's going to be trying to minimize, so he'll try to play along the lower envelope. Now, can they actually do that? Well, since they don't know the proportion of times that the opponent is going to play a strategy A or strategy B, no, they can't do it exactly, but they'll attempt to do it. All right, so now in an n by 2 game where Rose is selecting, wait, that's a 2 by n. Um, no, that's an n by 2. She will try to maximize by playing along the upper envelope in a 2 by n. Colin is selecting more than two strategies, and he'll try to play along the lower envelope. Excellent. All right, so how do we graph one strategy? Okay, so let's do this. Let's make row A the y-intercept value. And let's make row B the value where the line crosses through, where the strategy line crosses through the line x equals 1. And so what we're going to do is we're going to let x, all right, so the value of x, right, is going to be the percentage of time that Rose plays strategy B. So 100% A. So A is the y-intercept, right? And then as we go across, remember this is the percentage of times that Rose plays strategy B, right? At 1.0, that's 100% of the time. So that's why where we cross through the line y equals x equals 1, right? That's going to be the value in strategy B row, okay? So that's what we're going to do. And hopefully that will simplify things. It makes the graphs very easy to create, right? And we want to acknowledge just what I drew on there, right? That when x equals 0, Rose is playing A 100% of the time. So, right, at x equals 0, that's Rose 100% of the time, so it's a value of 1. And when x equals 1, right, that's a value of 5 because Rose is playing A 0% of the time there, right? 100% of the time she's playing B there. Okay, so getting rid of some of the mess. All right, and moving forward. Right, so notice how we put in the points, okay? So these are designed very specifically, right? Because I'm putting them in as an ordered pair of ordered pairs, right? Which means that this variable, points 3, right, it has both points in it. And the zip with the star and the points with the star, that basically zip will take a series of ordered pairs and zip them together into one object. And star zip will do the opposite. Will unzip a collection of ordered pairs into their single pieces. Okay, and what are we doing? Well, when we create them like this, right? Right, then this is the first ordered pair from P2. I'm sorry, that's the second. The first one, right? P2 0 is the first value from point 2, right? And then P2 brackets 1 is the second point, all right? So this zip and unzip is what makes all of this work, right? What does this function do? It just takes in the values of the 2 points and returns M and B, which are the values we need to write slope-intercept form. Okay, so now we have the slope and the intercept for this line. Okay, and this line, the one that goes through point 1 and point 2, which in our case, all right, is these 2 points right here, right? Okay, so that's why we're going to create the points in the way that we have here, so that they fit in this function, and this function is going to help us down the road. Okay, so graphing this one strategy again, and making the points, right? That the value from strategy A, right? The value of 1 goes here on the y-intercept. Where I go through the line x equals 1, that's where the value from row B goes. As we said, the value in row A is the y-intercept, and the value in row B is where the line crosses through x equals 1. Okay, So we're going to graph the three strategies the same way, right? And notice that we're going to put 2, 4, and 1 as the y values with the x coordinate of 0, right? And then we're going to put 1, 0, and 5 as the y values where where the x coordinate of that point is 1. And that gets all the values in the right places. All right. So how do we determine the active strategies? Okay, so there's only going to be two. And what's happening here is that Colin is the one that has three different strategies. And what he's going to do, Colin is going to try to minimize. So what Colin will try to do is Colin trying to guess what value of X that Rose would play is going to try to play along the lower envelope. He's minimizing and we're trying to play along the lower envelope. Okay, so what's Rose going to do? Well, Rose is choosing what percentage of the time she's playing A or B. So she's playing along the x-axis, and she's going to play along the x-axis in a way that she can get to this point here, right? That intersection of the red and blue is the maximum value on the lower envelope. So we know that Colin's going to do his best to play along that lower envelope. He's going to, guess his best guess of what Rose will do, and he's going to try to react to that and play along the lower envelope. Rose is going to pick the maximum value in the lower envelope, which is the intersection of the red line and the blue line, which is the intersection of strategy 1 and strategy 3. Okay? That's what they're going to attempt to do. All right. And again, here we have Colin minimizing, so we're playing along the lower envelope. So what are we going to do? We are going to graph this first of all. And like I said, the values 2, 4, and 1, they're going in the ordered pairs with the x coordinate of 0, right? They're going to be the y-intercepts. And then the 1, 0, and 5 from row B are going in the ordered pair where the x value is 1. They're going to be the value of that line where we cross the line, the vertical line x equals 1. Notice that we're zipping them correctly and putting them where we need them to go, so that they'll work with the function we created when we need to find the intersection. Okay. And by the way, just to explain where the values are coming from in the next slide, let's actually do the algebra, right? If I have two lines, y1 equals m1 times x1 plus b1 and y2, at the point of intersection, right, the x coordinates and the y coordinates are going to match. Okay, well, that means that if y1 equals y2, I can just set the right-hand sides equal to each other. All right, so setting the right-hand sides equal to each other, but notice the x coordinates are the same as well. So instead of writing x1 and x2, I'm just writing x, right? They're the same value, okay? So since we're solving at the point of intersection, right, the x coordinates have to match and the y coordinates have to match. So we're just using those facts to solve. And now what I'm going to do is I'm going to move all of the terms involving x to the left and the other terms to the right. Okay, so I have mx times 1 minus mx times 2, right? So we've moved the m2, sorry, times x over. And we have b2 minus b1. Why? Well, we've moved the b1 over. We've subtracted b1 from both sides, and we've subtracted m2 times x from both sides. And then we've factored out the x. Okay, factoring out the x, now we have a term that we can divide through by. Okay, so this is what the x coordinate's going to look like. Okay, so if I know the slope and intercept from the two lines, I can just do b2 minus b1 over m1 minus m2 to find the x value for the point of intersection, the x coordinate for the point of intersection. Then I just plug that x coordinate into either line, right? If I plug that x coordinate into y1 line, I'll get a value for y1, but it'll be the same value I get if I plug it into the equation for y2. And that's exactly the algebra you're going to see happening when we solve for this point of intersection, right? You can see, right, that what are we doing? Well, we said that the intersection of lines A and C, or lines 1 and 3, were that's the intersection point on the lower envelope that Rose is going to try to choose, right? So the x value is going to come from what? Well, this b2 and b1, these are the values that pop out of these two functions, right? We're calling this get slope intercept function, right? And the m values come from it too, so I do the same subtraction that I showed before, and then here I'm just putting in the values m1 and b1. So basically I'm using the line y sub 1 to plug the x value into and see what y would be. And the cool thing is when I find the point of intersection of these two lines, right, the x coordinate is the game value. Okay. The x coordinate, I'm sorry, I've got this backwards. This ordered pair is written backwards. V is the game value, that's the y coordinate, right? The x coordinate is the optimal proportion. Remember, for Rose playing strategy B. At the origin, she plays strategy B 0% of the time and A 100% of the time. At x equals 1, she's playing B 100% of the time and A 0% of the time, right? So we have a way to calculate her game value and the proportion of time she'll play B. If we want to know the proportion of time she'll play A, we'll have to do 1 minus x to get that.